И Дэвид, Вин, наш второй спикер, Дэвид Vandevoorde.
Good morning. Can you hear me in the back? Good. I come from the future. I've got some good news. Today, in your time, you're already the smartest, best-looking professionals in the world. Is going to get even better in the future. And more importantly, C++ will be even more fun to program. And today, I want to talk to you about some developments that are going on in the C++ community. C++ standardization committee. My name is, well, I can't read that. Yeah, David Vandevoorde. I work for a tiny company. We're 6 people. We're very involved with the C++ standardization committee. My boss chairs the meetings. My colleague has been there since the very first meeting way back when, almost 30 years ago. I have another colleague, she's the secretary of the committee. Another colleague is, he's a wiki master. And I'm on the evolution working group and on the direction group. So there's only 6 of us, but we have all these roles in the committee. I also wrote a book, a template book. There's a URL there if you're interested. The first edition was translated in Russian. The second edition is out, but it's not yet translated. Let's see if I have a remote here. All right, let's start. This talk's going to have some things that are a little bit fluffy, a little easy, and some things that are a little technical. If you get lost in the technical, it's not going to be very long. We'll move on to something easier a little bit later. I'm going to switch back and forth between different things. But first, I want to agree on what reflective metaprogramming is. I think you probably all know, but it's just nice to all have the same vocabulary, right? So reflective metaprogramming consists of 2 things. One is reflection, right? So what is reflection? It's the ability to look at a program in some sort of structured way. So not just a source code, but being able to query something about it, right? So some data model maybe. So imagine you have some code, it has some, you declared a structured type, has some members, you define the member, and maybe you have some more types. Well, you'd be able to ask your reflection tool, whatever that is, you'd be able to say, well, what is this? And the reflection tool will give you back some data that says, well, it's a type. And you say, well, what kind of type? And it'll give you more data, it'll say it's a struct. Say, well, since it's a struct, I'd like to know its members. And then it'll tell you information about the members and so on. That's what reflection is. Now, you could imagine a system that tells you everything about the program. You know, we don't necessarily aim for that. So reflection can be and often is incomplete. For example, very typically, reflection systems will tell you what S is, what its members are. It might even tell you that it has a definition, but it might not tell you what that definition is. Okay, so it doesn't have to be complete. And the other part of reflective metaprogramming, of course, is metaprogramming. So what's metaprogramming? Well, I like to say that normally we write the program, and you know that every computer science problem is solved by adding a layer of indirection. Well, this is a layer of indirection. So instead of writing the program, you write the program that writes the program. Right? So if you put the 2 together, you get reflective metaprogramming. And the idea is you start with some code that you wrote. You have some tools that actually look using, extract the reflection data from your code, and then you use the metaprogramming to, you direct it using this reflection data to generate some more code. In theory, you could make this a cycle, so you could, reflect the code you just generated and do another cycle on that. Usually, a single level is plenty. All right. Now, there's still some options in here, and the committee and I are interested in one particular set of options. First, you could have the reflection happen externally and the metaprogramming happen externally. So you could imagine that you have some external tool that looks through your code, collects a database, and then you have a script in some other language that generates code based on that. That would be external metaprogramming or external reflection. We're not interested in that. So we're particularly looking at the situation where the program looks at itself. It's all C++, up and down. And the second, oops, let me come back. The second distinction is compile time versus runtime. A lot of languages have runtime reflection. So the runtime system has a representation of the types of the program, and you can query at runtime. But that is not what I'm looking at either. know what the committee is looking at. We're looking at compile time reflection. So everything's going to happen at compile time, which is what you would expect, because as usual, C++, we don't want to pay for things we don't use. If you put it in the runtime, we don't know ahead of time what you'll use, and you then end up paying storage costs for the metadata. Now, of course, if you have it at compile time, you can develop a library to generate runtime reflection facilities, right? So you haven't really lost anything. All right. Today, the situation is not very good if you're interested in this. The answer is going to be template metaprogramming. And I'm going to talk about that in a few minutes, but first I want to go over some examples of things that we would like to solve nicely. Okay, and the most common one that you'll encounter is the idea of generating serialization functions. So you have some types, some struct types maybe, and you would like to send them over a wire, or you'd like to store them, and usually what you do, or what you have to do, is either use an external tool, or you'll write manually functions that transcribe it from the internal representation to some sort of persistent representation. Lots of work, easy to get things wrong, or your build system becomes very complicated. We'd like to be able to address that by giving you tools to, at compile time, traverse your types and maybe generate other types from it, other representations or functions that do a certain thing. We'll look at an example when we get into the more technical parts, an example that's a little bit related, where instead of generating a function for serialization, we will generate functions for hashing. Okay, second example is silly and happens all the time. How many people here program with enum types, enumeration types? Very, very common, right? So you say enum, your name, open brace, and then you start listing some names that have meaning, and each of these names has a value. But after that, you cannot get back to that name, right? So every time you use that name, the compiler just takes the value and forgets about the name. Now, sometimes you want to output those values, or you want to represent those values in some ways, and you already have a very nice name that you put in your definition, and you'd like to put the output using the name, not the value, because the name has meaning to a human. The value is just, some bits. But you can't do that. If you want to do that, you have to create a separate table that you have to maintain along with your enumeration type, and then do the mapping manually. So wouldn't it be nice if you could, as a compiler, well, just give me the name of this enumeration constant, and then output it, or store it, or do something else like that. Third example, this one is really interesting. We have in the committee now a subgroup that's interested in high performance and low latency. Now, yesterday I think I attended 4 talks, and 2 of the talks talked about traversing a vector of structs. And they talked about various ways of doing that nicely. But imagine you have a struct and it takes up a certain number of bytes, maybe 100 bytes. And you traverse the vector, vector 0, 1, 2, and you look for certain ones that have one data member of that vector has a certain property. Maybe it's equal to a certain ID. And for each one for which that is true, you have to take an action. Well, if you have a structure of vectors, you're missing cache every time, because they're 100 bytes away from each other, right? So you're looking at a field that maybe is 1 byte, because you just need to find out, is it the right ID? Nope. And then you go 100 bytes further on, so you completely miss the rest of your cache line, hit the next cache line, cache miss, and it's unacceptable in a lot of situations. So what a lot of high performance applications do is, instead of having a vector of structs, they have a struct of vectors. Now you still have the original struct of the data, and then you need to write functions that map between the struct of vectors and just the plain struct, right? And you still have to manually also define the 2 functions. Wouldn't it be nice if you had the ability to generate these things automatically? So you just, any struct, you say, well, give me the corresponding struct of vectors. And in addition, give me an interface on the struct of vectors that's a little bit like the vector of structs, so I can program more easily. Maybe I can use all the standard library algorithms for it, or the range functions. So that is something that the committee is one of the many problems that we have on our list that we want to solve using reflection. And then finally, and this is really interesting, and unfortunately I don't have the time to delve into it, so I'm just going to give you a link. But Herb Sutter, which you probably know, he's the convener of the committee. He's been, for the last few years, he's been looking at a problem called metaclasses. So he wants to provide a facility for you to be able to write classes more efficiently. Because often your classes are not just any class, it's not just a random bunch of members. It's a bunch of members for which you have already some structure. Maybe you have an interface type, right? And in an interface type, you won't have things like definitions of your virtual functions. All the functions will be virtual. Maybe you all have to be pure virtual. You have some sort of convention for an interface class. And you would like your engineers, even your junior engineers who come in, to not make a mistake with this, right? So wouldn't it be nice if instead of saying class X and then describe your interface, you'd say class, maybe parentheses interface, and then X, open brace, and you just have to declare things, and the meta program would make sure that it actually is an interface, and it would maybe add a few things, like it would automatically make everything virtual, automatically make everything abstract, and so on. It's a pretty advanced application of metaprogramming. You can find it at this URL here. And normally you should have either already gotten the slides or you will get the slides. I'm going to use, throughout the talk, a few of these URLs. How many of you are not familiar with wg21.link? Everyone knows this? Okay, I see a few hands. Let me explain. So the committee does most of its work through papers. So we write papers, we exchange them, we discuss them, we vote on them. We have different kinds of papers. These days, most of our papers are numbered with P and some number. And then every time we revise a certain paper, it has a revision. So it starts at R0, R1, R2. So Herb has made 3 revisions over his original. WG21link provides you access to any of these papers. So if you know the number, you can get the paper. Right? So if you know P0707 is what you want, just type that in. You can actually leave out the R, and then you'll get the latest version. So I'm sure Herb is going to update his paper. If you look in a year, just leave out the R3, you'll get the latest version. If you're wondering how much has it changed over the revisions, and it has changed a lot, just put R0 here, you'll see the original one. All right? Okay, so that's for what we want to do, a few examples. There's many more applications. I'm sure you guys have some. Now I'm going to give you a taste of the present, which is not very good, so you appreciate even better the taste of the future, or the taste of the future that I imagine. So I'm going to talk about template metaprogramming, which is sort of a hairy part of C++ programming. How many of you have done some template metaprogramming? A lot. Okay, you guys are specialists. So I'm not sure this is going to be very helpful, but I just didn't want to make any assumptions. So we're going to move quickly through a few ideas in template metaprogramming, and then I'll tell you about some of the problems. So when you perform template metaprogramming, what you're doing is computing with types, and the computational engine are templates. So the basic component of template metaprograms is a class template that maps the template arguments to here we go, to this thing here. So you conventionally you choose a name that is the result of your meta function. A meta function doesn't take an ordinary value. The values are all types. Okay, so this is a meta function add pointer t, which turns t into a t star. You can create an alias for it in C++11. It just makes it convenient to avoid to have to replace to use type name : type everywhere. But then you can apply to a type. So if you start int, you could apply a function, you could apply it again, and now you have a int star star. That's trivial, right? Now, you can start composing this. You can even have, since we have template parameters, you can create functions that take functions. So here, I made a repeat function which takes a meta function, so a template parameter f, and applies it to t n times. Now, in my slides, I've used int for the numbers, but template metaprogrammers often use types even for the numbers. They wrap them in more types, but for conciseness, I've just used int directly. So how do we do that? Well, we do it recursively. So applying it n times means applying it n-1 times, and then applying f one more time. Hope that's somewhat clear. Now, how do you stop the recursion? You make a partial specialization for the 0 case, where since you didn't apply f at all, you just return t. Okay, I can wrap that, so I can apply repeat on my add putter that I had before, right? So now I have a shorthand to get, instead of one putter, I can add n putters. Right? So I can here, for example, I apply it 4 times, and so instead of getting a pointer to a pointer to int, I actually get a pointer to a pointer to a pointer to a pointer to an int. Not very useful, but that's how it works. Now here's the bad news. I'm a compiler writer, so I can tell you quite a bit about how C++ compilers work. We never deallocate memory for types. So once you have a type, it stays there forever. Types are not just 3-4 bytes. Your typical type, like a little type like that, will take a couple of kilobytes of representation in your memory. Okay, so what we have here, right, is 5 instantiations, sorry, right, for n equals 0, 1, 2, 3, 4 of repeat, and equivalently for add and putter. Right, so so we actually have already a whole bunch of kilobytes that have been allocated in your compiler, and we'll never release. Now, as you say, well, it's fine. I've only gotten, maybe 10 types complete here. I can afford that. But of course, we don't program with single variables and single values. Usually, we have containers. So for containers, we use variadic templates. Right, so this is a type container seek. You can just put types in there, and we'll treat them as containers in our metaprograms. Now, we'll want a function, a meta function, that given a seek and an index will return the type at that index. I'm going to show the one implementation in the next slide. It's going to be the most complex slide of this talk. I hope I can get most of you with me at that point, but we'll have this function in the next slide. Again, you can have an alias. Now, it's very useful when you deal with template packs, right, with variadic templates, to have a sequence of indices. So I'm creating a class here, valseek, which is a sequence of non-type template parameters. And I can choose a type, but I'm going to choose int. Okay, so I have an alias here. I call it index set. That just means a template instantiated over value. So you could say valseek int 3, 4, 22, and so on. Now, even more, one of the most common cases of that is that I actually want the case 0, 1, and so on to n minus 1. I just want to count. Okay. Now, if you do this recursively, how many instantiations will you have? Right. So if you want to recursively build an integer sequence with n items, how many instantiations will you have roughly? Order of. Anybody have an idea? You'll have about n instantiations of each, about n arguments. So how many arguments we have on average? About n squared over 2. Right? Your arguments each take a certain amount of space, right? Maybe 100 bytes. So now you have a quadratic increase in compiler memory. Because of that, and because the standard actually has a similar class in the standard, several compilers, including Clang, Microsoft, and our compiler, the EDG compiler, have this primitive called make integer seek. And what it does is it quickly creates one of these class expansions with arguments 0, 1, and so on to the value that you choose, n. And you can actually choose whichever template you want. So I use valseek, but in the standard is integer sequence. So there's a function called make integer sequence that does this. Now I'm bringing all this here because I'm going to implement index t in a non-recursive way. Why non-recursive? Because if I did it recursively, I would again get into that n square problem. And if you start making long sequences, every time you try to get one element out of that sequence, you would use a megabyte of memory or more. Right? We don't want that. So here is the most complex code we're going to deal with. First, I have a very simple class, it's a meta function, right? It just maps t on t, so it's identity. The reason why I need that is I'm going to create pointers to types, but if it's a reference type, that would be invalid. So I'm just first going to wrap my type into this identity, and then I'm free to put a pointer on top of that. Next, I'm creating a class indexTHelper, which is going to have this member function f here, right? And that function has a funky signature. It does decal type skips, and skips is this template parameter here that's variadic. Okay, comma void star 0. Okay, what's the type of this decal type? Shout it out. void star. Okay, so we have a void star. So all we do here is void star, but I did a skips here. What is skips? It's a template parameter. It's a variadic template parameter, and I have a dot, dot, dot here. So what's the effect of this? It creates skips number of void star parameters. Okay. Then I have a t star here, which is actually the template parameter of this. It's a function template. So it's deducible. And then I have a C-style variadic thing. This can accept any number of arguments you want. All right, so now I'm writing my index T. And I'm specializing it for any I, and specifically for the seek class that my container class in my metaprogramming for T dot dot dot. So what I'm going to do, I'm going to invoke this helper with a make index set, which I have a special built-in function for, of I. Okay, so what I'm creating is, by calling it with that, I'm creating a pack of I elements, right, 0 to I minus 1. I instantiate it over the skip, so now I have I void stars, right, from 0 to I minus 1. And then I'm calling that with identity T star, just cast to 0. I don't really care of this value. I just want the value of the star expanded. So I'm taking all the types from my sequence, and I'm creating null pointers that are null pointers corresponding to the types wrapped in identity of my sequence. So that will be a match for this, but the only one that gets deduced is the one in the ith position. So because I deduce it, the return type becomes the corresponding identity type. So I have now almost the type that I need, the ith type. I can just do a decal type of that call. It gives me identity of T, and I do colon colon type, and I have a type. I realized this was a quick walkthrough, so it might take some time to let this sink in. But my point is not, this is a great technique. My point is, this is terrible. You don't want to program that way, right? If you have to understand this to just do an array indexing, my gosh, we don't want to program that way. But this is actually done in practice so that we can go over sequences a little bit more efficiently than recursively, right? It's order n instead of order n square. All right, so how do you do reflection in metaprogramming? This is a little easier. It's just one example. Say you want a meta function that determines whether type T is a function. Well, by default, we'll say it's false, and we'll say it has no classic varargs argument. And then you do partial specialization. So there's a partial specialization for a function type with a return type RT, and then this is a variadic parameter, so you can have any list of parameters. And if it matches this pattern, then the answer is yes, it's a function, but it's not a varargs function. If in addition to the parameters you also have comma ellipses, then it's a varargs function. This just handles the case of non-member functions. If you want member functions, you're going to have to specialize this for const volatile, ref, non-ref, and every combination you can think of. Not difficult, not beautiful, takes a fair amount of code, and now you have to do this for all kinds of types. But you can do a little bit of reflection that way. That's the only way we do reflection today in C++. Sphere. How many of you know what Sphere is? That's great. How many don't? Okay, so I will go through this a little bit. I hope I won't lose you too much. Sphere is a term that I invented about 15 years ago in the first edition of a templates book. And it's gotten very popular. And what it means is that substitution failure is not an error. So what is substitution? When you write a template and you use it, the template is instantiated. It means that, for example, from a class template, you create a real class. If anything goes wrong during that process, you get an error. That's called instantiation. It's called an instantiation error. But once in a while, the language requires a compiler not to instantiate, but do a trial substitution. Just try out these arguments and see if it works out. If it doesn't work out, if there's an error occurs, in some circumstances, it's not actually an error. You just sort of throw away that possibility and you try some other possibility. Particularly if you have overloaded functions, maybe some other overloaded function will match. So there's a little tool that was developed by Jaakko Järvi based on this idea in my book called enable if. And what you do is you declare a structure that takes a type, arbitrary type, and a condition, but you don't define it. See, there's no definition for enable for the normal template. But for the specialization where the condition is true, you do define it and you just return the type. Okay? So if you try to access the type of enable if, it will work only if the condition is true. If the condition is not true, then it's an error. But as I said, errors are not always errors. Okay? Now, I just have an alias. This alias is just to make it easy and to avoid having to write type name all the time. Say I have a pack function. So I want to have a function that takes an one of the sequences that we had earlier over an arbitrary number of types. But I have two versions of my function. I have a different version depending on whether the length of that pack is even or odd. Well, if it's odd, the size of here, so the size of modulo 2 is going to be non-zero, so it'll be true, right? So this enable if here, if the length is odd, will be fine, right? So it will actually return the Can you hear me? Woo! Thank you. Okay. Thank you. Well, I'm glad you guys stayed. Thank you. So we went through this. Basically, here are two functions that are absolutely ambiguous, right? They have the same template parameters, but Sphere allows you to still disambiguate them by having the return type depending on some condition that is mutually exclusive. Right? So in this case, you can make this function work for odd length sequences and this one for even length sequences. These days, this is used everywhere. In particular, the standard relies on it everywhere. I'm going to skip a little bit faster, so I think I'm going to skip this slide. But there is this notion of expression templates, which allows you to take an expression, and instead of evaluating, you represent it as a type with some references to storage, and you only evaluate the expression when you process the equal sign. So with template metaprogramming, you can basically make vector operations that are very efficient, no temporaries. It's just as fast as, I mean, if you have a good optimizer, just as fast as if you were to write the loop by hand. So it's also a form of reflective metaprogramming with templates today. Anyway, we're through the most difficult part of the talk. My main goal was to sort of convey how bad the situation is, right? So it takes up a lot of memory. The programming is not intuitive. It doesn't look at all like other C++ programs. You don't compute with values, you compute with types. It's not great. But we do it anyway because even though it's not great, it's useful, right? We really like to do certain things at compile time. We like to synthesize code by instantiating templates in odd ways, and we like to figure out what our types are and act differently depending on their structure. All right. So now that we've been traumatized by this, let's relax a little bit and talk about where we came from, how we got there. Right. It's actually the 30th anniversary of templates, of the public presentation of templates. Bjarne Stroustrup, the inventor of C++, from the start wanted generic programming as part of C++. But at first he thought macros would do it. So in 1982, you could actually find papers where he said, you know, we really need generic programming. I think we can do it with macros. Maybe we'll need a little bit changes, but it will work. And then a few years later, he said, no, it's not going to work with macros. We need something more akin to templates. So in 85, 86, you can see the first references to the idea of we need something like templates, but he didn't have a design in place. But in 1988, we get the first paper called Parameterized Types for C++, which actually presents templates pretty much like we have them today in the simplest form with many fewer features, but you had the angle brackets, the template keyword, and so on. This was at a Unix conference in Colorado. So that's 1988. The standard starts the next year, and then how many people have had this book or a Russian version of it? This was my favorite book growing up. This is my second C++ book. I read it front and back. I learned it. This was the Bible of C++ during the early 90s. But what was interesting is this is the first time that a book described templates. If you went to the appendix of this book, it described both templates and exceptions. They were completely new things at the time. We still had no implementations. We're talking 1990 here, right? 2 years after Bjarne proposed this design, there's no implementations. It's only the next year that Cfront, which at the time was a compile that Bjarne had started, but he was no longer really working on it. Now AT&T had taken it up, and unfortunately this is unreadable. Let's see if we can zoom in a little bit. Yes, we can. I don't know if you can read this far, but this announces C++ 3.0. Now, I don't know if you know what C++ 3.0 is, but back then there was no standard. The standard process had just started. And so instead of referring to C++ 98 or 3 and so on, they refer to C++ according to the version of the AT&T compiler. And this was the version 3 of the AT&T compiler, which provided things like templates. There's this whole article, which is in a mainstream article about computer industry. You know, it talks about templates, it talks about generic sort, and it actually talks about some companies that work with AT&T. And what very few people know is that there was a company back then called Object Design. And Object Design made the very first implementation of templates and contributed back to the AT&T subsidiary that distributed Cfront. That's a little trivia for you. Now, anyone has used Cfront in this room? Anyone has used the early compilers of the 1990s with templates? Not fun, right? I mean, it was the first compilers, C front and others, were quite buggy. If you tried to instantiate something, you had linker errors almost guaranteed because the things you thought would be instantiated were not getting instantiated and so on. Well, this is a compiler that changed all that. BORLAND C++ 4.0 was the first that was solid enough that a whole bunch of techniques were developed on this. Right? This came out in 1993. 1994, ERWIN UNRUH actually invented metaprogramming, or he observed metaprogramming. He said, "Wait a minute, this instantiation thing, that's kind of neat. I think I can generate prime numbers with that." And so in March 1994, the committee got together in San Diego, and he worked with one of the compiler writers there called Tom Panello. He had another fairly good compiler called Metaprogramming High C++. I don't know if any of you used that. But he made the first metaprogram, and he showed it around to the committee, and people were like, "Oh, that's neat. That's probably not useful, but it's neat." Let's go back to BORLAND C++ 4.0 here. There's a few things that were done for the very first time on this compiler. STL, anyone has heard of the standard template library? When it first came out, the only supported compiler was this compiler, BORLAND C++ 4.0. Expression templates, this technique I mentioned earlier, this compiler. Template metaprogramming, not as a trick to generate error messages with prime numbers, but as a way to actually generate code in your program. First done on this compiler. Wrote 2 articles that explained expression templates and metaprogramming in 1995, so about a year after we discovered these techniques. And both of those articles mentioned, well, my code runs on BORLAND C++ 4.0. So really a turning point in the world of templates. For the first time, people started using them for real in fairly large scale with reliable results. Anyway, in 1998, we have ISO C++, the first standard. That was an exciting moment. Actually, we finished in 97. But ISO bureaucracy required a little bit more time before it was published. Now, ISO C++ had almost no acknowledgement of metaprogramming. So there was no use of SFINE, there was no real metaprogramming. There's one thing that had a little bit of acknowledgement in there. It's very obscure reference, but if you look in the specification for VALARAY, there's some paragraphs there that they seem to not say much, but in fact they're an allowance for using expression templates in them. And those paragraphs, I just checked yesterday, they're still there to my surprise. Anyway, remember Andre yesterday? In 2001, he came up with this book, or this book. It changed the world in terms of thinking of metaprogramming as something you can actually design with, right? So TODD VELDHUIZEN had shown that you could do high-performance computing with it, and so it became a little bit popular among the people who write scientific numerical codes. But it still was not widely known. But in 2001, Andre really made a beautiful layout of how you could put things together to actually make useful code, not just for numerical application, not just for high performance application, but just to get your code more compact, more reliable, and more easy to write. Okay. When that book came out, I had been working on a book for templates, and so I was quite jealous because I thought he'd made a better presentation than mine. But anyway, the next year, I published mine with the help of Nico Yuziris, and it explained templates, it explained metaprogramming, but it's also the book that introduced SFINE. Right, so we talked about SFINE earlier, so this was also, these 2 books together, I think, helped change the direction of libraries like Boost. Before these books were there, Boost didn't do a lot of metaprogramming, but after that, just about every library takes advantage of these template tricks to do things a little more efficiently, a little more generally, and so on. Okay, now, SFINE is all well and good, but it's hard to use, so that enable if component was actually invented by Jaakko Järvi, Jeremiah Wilcox, Howard Hinnant, and Andrew Lumsden. Jaakko is a person that brought us lambdas in C++, among other things. And Howard Hinnant, you probably know, he's the guy who brought us move semantics, and recently he also brought us calendar functions. So C++ 11 is a completely different beast from C++ 98 if you look at the library. It's got enable if all over the place. Well, it doesn't actually say that. It has some magic words that basically require library implementers to use enable if, and there's also various places where all the kinds of metaprogramming are needed. Language doesn't stop. We get a few more features, and we get C++14. Now, the fundamental properties of template metaprogramming in C++14 and C++11 are not that different. But these couple of additional features actually allow you to change the way you look at them from the user's perspective. And someone called Louis Dion created BOOST.HANA. Anyone here familiar with BOOST.HANA? Anyone has looked at that? I really have a room of experts here because I see a lot of hands. That's awesome. Louis Dion is a fantastically talented person, good friend. And if you haven't seen BOOST.HANA yet, I recommend you check it out. It's pretty nice documentation and introduction. And it presents metaprogramming. It's still template metaprogramming, but to the user, it looks almost like regular programming. So it's a little nicer. At least the interface, the user model, is a lot better. It's still horrible for the compiler. It still takes gigabytes of memory to compile anything non-trivial. If you can compile it at all, you'll probably run out of memory. Okay, so that was our history. Now we're going to talk about some generalities. Louis Dion, the guy from BOOST.HANA, and I wrote this paper, P0633R0. And it's more of a philosophical paper. What we said is, there's really three choices we have to make when we design a reflective system. The first is, how are we going to do reflection? We already saw how you can use template specialization or maybe deduction to decide whether a type has certain properties and so on. But it's not very powerful. We need something much more powerful. So we will have to make a decision how we're going to do that, right? So we don't want, in template metaprogramming, it's just templates, but we want something a little bit more powerful. Second, we want a way to generate code. We want metaprogramming, right? And also something called reification. Now, what is reification? It comes from the Latin word for res, meaning a thing, right? And reification basically says, if you have some data representing some reflected entity, so you have a data representation of, say, a type, you want to turn it back into a thing in your program. So if it's a data representation of a type, we want to turn it back into a type. If it's a data representation of a namespace, let's turn it back into a namespace. If it's a data representation of a data member, let's turn it into a way to access a data member, and so on. That's called reification. It's sort of part of synthesis, but specifically how you connect to the reflected data. And finally, we actually need a way to control things, right? In template metaprogramming, the control is recursive template instantiation, which is terrible, and things like specialization to do selections, right? But we want something better. All right. Just before C++14 was published, the committee started a new group on reflection called SG7. There's a guy called Chandler Caruth, very talented also, chairs this. And very early on, they put out this paper, N38114. Papers used to always be numbered with N. Those are papers that, but nowadays only the ones that are for the official ISO processing have the N numbers and the others have the P numbers. So if you wonder why there's two different kinds of numbers, that's why it is. But N3814 was basically a call for people to look at this problem, and it had sample problems, including the ones I had at the beginning, things like serializations, enum transformations, and so on, and said, okay, we want to solve these problems. And a guy called Matusz Chochlik, I probably mispronounced his name, but he came up with a grand proposal that has a lot of ways to do reflection. You can look at a class, you can ask for its members, you can ask for the parameters of a function, and so on and so on. A lot of useful information. And the way he did that, he says, well, since we have template metaprogramming, I need to express that as types, right? My meta information, since template metaprogramming is operating on types, my meta information has to be types. His original paper is this one, N3996, and you can see he actually started it before we switched to the P numbers. So it started with N3996, showed it to committee or to SG7, the SG7 part of the committee. They liked it a lot. Some other guys started joining, so Axel Naumann and then later David Sankel joined, and they've been refining this proposal. There's actually 10 revisions of this paper. If you include the 396, a couple of other N papers, and then the P0194 papers, there's 10 revisions of it. And this is actually going to be a TS fairly soon. But let's take a look at how it would work. First, they're introducing a new reflex per operator. So you can say something like reflex per parentheses, a type name, And what does that return? Well, since they're doing template metaprogramming, it returns a type, another type, right? So if you apply it to a structure S, it gives you a meta S, and the structure of that type is useful for finding out things about S. It has a rich set of meta operations. So once you have one of those meta types, you can apply meta operations to it to find out things about it. For example, if you have a meta type for structure, you can apply another a meta function, which will return another type that describes the members of the function. And then you can apply another meta function that iterates over the members, and then you can apply another function, and so on. I'm going to show you an example to make that a little bit more intuitive. But anyway, this ties naturally into template metaprogramming. It also ties well into BOOST.HANA, which, remember, is actually based on template metaprogramming. And Louis Dion, the author of HANA, actually did a lot of work to prove that it all works fine. So that's why SG7 liked it. Now, the reification, the turning from data back into constructs from your program is a little limited. You can certainly create pointer to data members, for example. If you have a description of a data member, you can create a type, but you can't, for example, create a namespace because there's just no way to do that with template metaprogramming. They did think of, oops, what did I just do here? Sorry about that. They did think about the idea of an unreflexper operator, but actually it's not technically feasible. They're not compilerized, and so it wouldn't have worked, at least not the way they expected it. But anyway, the basic facilities are scheduled for TS, so that means that compilers and library writers are encouraged to implement that so we can try it out and find out if that's really what we want. Now we actually know that it's not exactly what we want, but what we hope is that we'll find out whether the actual data we can get, so what are the facilities overall, we would like to know that that's really what we need. Here's an example of code using that TS. And I'm going to use that example over and over throughout the rest of this talk. Okay. So what are we going to do? We're going to create a hash append function, which automatically creates a hash function for a simple structure. So this is using, just a sec, this is using concepts, as in 2020 concepts. If you don't understand concepts at all, just ignore this line. It says requires. It's just a constraint. It says that this S has to be a simple structure. It means a structure where it makes sense to just iterate over the individual members of the structure. And H is the state of your hashing. So hash append is just a way to get more and more bits into your hash function. So that state gets passed to hash append, and the structure that you want to hash gets passed as well. So what does P0914 offer you? Well, first, the reflexper operator. Reflexper returns a type that describes S. In this case, the S is a type that you're trying to hash. Right? So now you get a meta type. We don't really know what's in that type. We don't really need to know what's in that type. We just have functions to apply to it. And remember, these are meta functions, so they're actually templates. Right? So there's a get data members template, which turns that meta type into another meta type that is a collection of information about the data members. And then they have a really powerful meta function, which is for each. Now, there is a for each in STD. This is different for each. First, the collection you iterate over is not a regular argument. Since we're doing metaprogramming, it is a type, right? It's a type that describes a collection. So for each is then going to instantiate the thing that you pass as a real argument. The thing these are regular parameters. It's going to instantiate that over and over for each data member. So in this case, we're passing a generic lambda. That's convenient. We don't actually care about the value that is passed in here. So we're passing an auto meta member. We really don't care about the value because everything is types. We care about the type. So let's take the type of this meta mem is decal type. Now, what is decal type of meta mem? What kind of type is that? Anybody? It's not a class type. It's actually a reference type because it's an L value. Okay, so we need to get that reference off there. There's various ways of doing that, but one of them is just you can do : : even on a reference type if it's a reference to class type. So you can do : : and it turns out that these meta types have a : type in them that gives them self back. So that's just so what you see here is just a quick way to get the type of meta mem, the class type, not the reference type. Okay, once you have that, there is a REIFICATION function here that, given a meta mem, returns a pointer to data member. So now I have a pointer to data member describing a particular data member of S. And I can just recursively call hash append on an access of that pointer data member. So this dot star here is for accessing data members. Hope you're still with me. So this is pretty neat, actually, right? We cannot do that today in C++. But with P0194, you can iterate through all the members of a structure, for example. You can do a lot of other things. You could iterate through all the parameters of a function and various other things you can do. So it's nice, but there's a couple of downsides. One is it's really not intuitive to compute with types. I don't know about you, but I usually compute with values, right? Ends, values of structure type, values of enumeration types, and so on, pointers maybe. It's not that intuitive, and having to move between the two worlds all the time can be quite frustrating. Second, the notation is kind of strange also. You know, angle brackets, parentheses, you have to remember which one to use all the time. Not great. But in fact, those two problems are relatively minor. The one that really kills it is the next one. This is template metaprogramming. We're going to instantiate tons of templates, and each of these instantiations, I mean, these meta types, they're not little itty-bitty types. They actually have tons of members in them. This is going to take megabytes, just that hash function, and one instantiation of it's going to take probably tens of megabytes to implement. You know, you can compile itty-bitty programs, and then you run out of memory. So I wasn't very happy when I learned that this was happening. So I came to the committee and said, wait a minute, you guys are doing metaprogramming. I don't want to do metaprogramming that way anymore. I want to do metaprogramming with values. So I wrote this paper, P0598. And it's not actually a proposal. What it just says, or a fleshed out proposal. It just says, you know, there's really disadvantages to doing things by instantiating templates. Let's do it with const expr functions instead. Right? We can now compute with values at compile time. Since C++14 we can do almost everything that you could do at runtime at compile time. Not everything, but a lot. Right? And a part of my talk is going to be to extend that even further. Right? So what are things going to look like? Well, instead of having all these meta types, we'll have one type. Right? I'm going to call it meta info for reflected meta information. So if you ask for the reflection of a class, you'll get a meta info value. If you ask for the reflection of a function, you'll get another meta info value. If you ask for the reflection of a data member, you'll get yet another meta info value. There's small types that can be used in const expr evaluation. I'm going to use const expr evaluation for control. Right? So now I have decided, remember there were 3 axes to reflection. You have to choose a way to do reflection. I'll use a single type. Control, const expr. Const expr is very efficient in the compiler. When you're done with it, it takes no memory at all. Right? All the memory is released. The code will look like regular C++, and you'll see it fairly soon. And like I said, values, you know, when you compute with values in the compiler, those don't stay. So types we have to keep forever, but values you know, if we don't need them, we can deallocate them and reuse the storage. And I proposed this, and the committee agreed. They said, okay, we agree that this is the way to go forward. We'll still go forward with this other thing because we're interested in getting feedback whether all these different meta functions are actually the kind of functionality we want. But the way we're going to go forward in the longer term is sort of this technique. Now, Louis Dion, who is a BOOST.HANA guy, has already done a lot of work in this space. He said, well, I'm really excited about this. I'm going to explore how to do this in real applications. And so he's looking at that from that point of view. And Herb Sutter, his metaclass proposal, the original proposal had a lot of things that he created from scratch. And he decided, well, this looks so good, I'm going to rebuild it on top of that. And Herb is working with Andrew Sutton, who is implementing Herb's metaclass proposal. And because Andrew Sutton says, well, since we're building on top of yours, I'm going to implement your stuff also. So he's got the same ideas, he's actually implementing it. And if you look around on the internet, I think you can find a Clang version that has some of that implements a lot of what's presented here. Right? The discussions about his implementation in P0993, and I think it might have a link to the repository of the Clang fork that has that implementation. By the way, Andrew Sutton is a person who is bringing us concepts in C++20. All right, now remember there were 3 axes, and I only mentioned 2 axes so far: control, const expr, reflection, a single type. The thing that's difficult is how do we do synthesis or reification, right? In const expert, you can evaluate things. You can't really have, today you cannot really have side effects, right? And reification synthesis is a kind of side effect that would have to happen during const expert evaluation. So we're going to need extensions for const expert evaluation. And I'll discuss some of those in the slides that come. So here is how the example that we saw with the P0194 with template metaprogramming, how it looks when you use the new direction that SG7 is looking at, right? You still have the exact same declaration of the function, but now I'm just going to run a for loop over the data members as values. Now, the first thing to realize is this has to happen at compile time. We don't want this to run at runtime. So there is a new construct called const_expr, open the brace, close brace, and whatever is in there, it gets evaluated right then and there as a constant value, right? You can put that inside a function, but you could also conceivably put it inside a class or inside a namespace. So as a compiler parses, if it sees one of those const_expr braces, it parses that as if it were sort of a function or a lambda, and then it immediately executes it, and it has to be, it has to successfully execute. If there's some value it cannot resolve at that point because it's only known at runtime, you'll get an error. All right. We take back the reflexper operator, right? But instead of it returning a meta type, it returns a meta info value. When I apply data members on the reflexper of a structure, I get an array of values, or maybe a vector of values. And we'll talk about the idea of using vectors in const_expr soon. Anyway, this is just a regular range-based for loop. Just execute it at compile time. And now I need a way to generate code. And in this particular example, and this is a point of design that's still being explored, I'm using a special operator called an injection operator. You see it over here, it's that little arrow. What this does is all the code that follows the arrow, and actually there should be a semicolon at the end here, I'm missing it, sorry. So all the things between the braces, including the braces, is going to be inserted virtually. The compiler will see it when it's done with this evaluation. So when it's done with the const_expr evaluation, everything it did here is going to parse. Now what did we do? Well, we went to every data member and we injected hash append h, s, and then we have m, which represents a member, but it's represented as an m as a data, but I need it as a thing, as an actual member. Well, there's a special operator, paren dot, and then dot paren, so surround it, that turns it back into an expression, right? So now you have, it's as if you had said h, s dot first member, and the second time around dot second member, and that all gets injected here. When the compiler is done with this evaluation, it will suddenly see these declarations. Internally, of course, it doesn't actually modify your source code. So that's how it works. And that's going to be the general idea of moving forward with reflection. And so when are you going to get this? I don't know. Are you going to get this? I'm not sure, but I think you will. My guess is C++23 will have this. You'll see some of the work already in C++20, and I'll talk a little bit about that soon. Let's talk a little bit about some of these choices. So what is meta info? It actually has to be a relatively small type usable in const_expr, and not only in const_expr, we also would like it to be a valid template argument. It's convenient to be able to instantiate template arguments over a meta info. What it actually represents is an index into the compiler's internal structures. If you're a little bit familiar with compiler design, you know it has something called an AST, abstract syntax tree. It's a tree that represents the meaning of the program. This is actually, whatever this meta info is, which is an opaque type to the user, it represents an index into that tree. Right? So if you have the meta info for type S, it is sort of an indirect pointer to the representation of S in the program. It could actually be an enum type, and that's how I expect to implement it myself. Oops, things are shaking. Ideally, we would like meta infos never to show up in runtime. And we think we could devise some rules to prevent that. But there would be complicated rules that you have to think about. If they're enum, it actually doesn't hurt if you make them go into runtime. If it happens in runtime, they have no meaning there, but it won't make your program crash or anything. You just have these meaningless enum types. And again, meta info or of its equivalent is discussed in the paper by Sutton and Herb. How do you get the meta-info values? Well, you already saw it. You can either use the reflex-per operator to get the first one, and then you can apply regular immediate functions to meta-info. Now, what's an immediate function? It's a function that is always evaluated at compile time. We don't actually have a construct like that today in C++. We have something called constexpr, which is possibly evaluated at compile time, but it could also be at runtime. So we will need something a little better than that. But anyway, you could actually inspect meta-info itself as a meta type. So you could actually reflex-per on meta-info itself, and now you get a meta-info of meta-info. And since it's a meta type and an enum type probably, it has a parent namespace, so you can ask for its parent, and now you have a representation of the parent namespace of T1. So that's how you can get more and more meta-info. You can kind of pull the thread of your program, find out what's there. Now there's an interesting question. What if you call for the parent of a type that has no parent? What should we do? Should the program be an error right away? Should it just return a value that represents, well, I don't have info here, you know, some sort of null value? Or should it be a sort of a Sphene error? Right now, we're actually inclined to go the Sphene case. So in other words, if you were to do this, parent of would come back to the compiler and say, this is not a constant. And if you use it in a signature of a function, that would just create a Sphene error. So you know, if there's no other candidate, you'll get an error, but otherwise maybe there's some other meta computation that can take over. It's an interesting little detail of the design. We'll see how that works out. And should there be containers and ranges of meta info? Absolutely, right? We'll be able to, we absolutely want ways to have big collections of things that describe parameters or meta functions or even types or everything that's in a namespace. So we'll need a way to have ranges and containers in constexpr. Now the functionality itself is guided by P0194. So we're not saying, well, we want a different set of reflected things. We'll have the same set, we just represent them differently, more efficiently, and you compute with them just like you do regular C++. All right, so how do you turn those meta info values back into things in your program? You already saw some, but let's, for notation wise, let me call I some meta info value. Well, if you need a type, you just say type name parentheses I, and you have a type. You need a namespace, namespace parentheses I, you have a namespace. If you need a template, same thing. Then you saw the one for an expression. Right now I'm proposing this notation. And none of this is cast in stone. There's general agreement that these are nice, these three. This one we're still sort of looking at. There's a third case, which is template argument. Why are template? Oh, first, the reason why we need to distinguish this, and this is why unreflex-per doesn't work, is that when you parse something, when the compiler parses something, before it even knows what the thing is, it has to know what kind of thing it is. That's why you have a type name keyword in C++, right? We have to know that something is a type before we can parse x star y. You know, if x is a type, then it's a declaration of a y pointer. If it's a value, then we have to, then it's a multiplication. So we need to know ahead of time what kind of thing we're dealing with. So that's why we have different reification operators for each kind of thing. If you apply it to something that's not a type name, you'll get an error. Right? So the compiler will say, oh, you're asking for a type name, but what I have here is a data member. That makes no sense. You'll get an error. Same with expressions. But there's one context where you can have any of three things, which is template arguments, right? Template arguments are usually types, but they can sometimes be class templates or alias templates, and they can sometimes be non-types. So there is a special notation to say, well, I turn that back into a template argument. And it could be any of these three things. So it could be an expression, type name, or template. More interesting, if you have a range or container of these things, instead of producing one type, one expression, one template, it will produce a pack. And you'll be able to expand that pack. Right? So for example, suppose you have an I that represents tuple of int short long. Well, you can ask for the argument of it by saying template args of I, and then you can instantiate those arguments with ... and now you have an S that corresponds to your tuple, right? So in short, long, you would have it right there. There's a way to just move template arguments over from one place to another very quickly and very efficiently. no recursive template instantiation. All right, for synthesis, you already saw one, that injection method. This is the most controversial part of this. So when we present this to SG7 likes everything that I've shown you so far, except this, or rather some of this. So that injection operator I showed you, it's convenient. For example, Herb Sutter counts on it for his meta class proposal, but it is controversial. It doesn't necessarily have support in the committee. Now we can actually do without it. We can do, just using those reification operators you've seen and template instantiation, we can do something quite useful already, and I'll show you how soon. So it's feasible, it's limited. We could perhaps extend it to do more kinds of generations. An interesting one, the first one I proposed, was actually to just be able to generate strings. So at compile time, you create C++ code as a string, and then you say compile this, right? And so the compiler inside would then start, instead of compiling from your source, it would compile from the string. That is highly controversial. It's very powerful. You can do really neat stuff with that. It's a bit difficult to debug, because if your strings are wrong, you don't actually have something to look at in your source. You just have a program that generates string. But I'll show you how it could be done. And then the token stream injection is the example you already saw with that arrow operator. I think it's powerful and readable, but as I said, it is controversial today. All right. I'm going to show you the example that we have had so far with those 3 different synthesis methods. Okay, so you understand what can be done. And the first one is, I'm just using the reification operator, so that, here I just have that members. I'm just using that dot parentheses. Now this time around, so remember previously we had a for loop that went over the members and we would call hash append, inject hash append every time. This time I don't do that. I just create a members variable, which is a container of meta info, right, for each member. I immediately on that container apply my reification operator. So now I have s.member, except because members is a container, what is this? It's a pack, right? So this is actually a pack expression. And if you know C++ 17, let's see here, then this is a fold expression. The thing that's here is actually a comma expression. You have to parenthesize it, and when you do dot, 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 you basically repeat this expression, comma separated, for every member of the pack, and every member of the pack is every data member. So this is actually a very compact way to do what we did before without a for loop, right? Without an explicit for loop. I happen to think that the for loop is more readable in this case, but we can do it without having the injection primitive. Right? And as Louis Dion has been exploring what we can do with this, and it turns out it's a lot. So if we don't get the injection primitives from the committee, we will still be able to do a lot of fair and nifty stuff, but the programming will be a little less clear. You won't have easy loops like that. All right, inserting strings at source. It's like the original case, so you have the const explorer again. You again have the for loop that goes over, but instead of having the arrow operator that shows you exactly the pattern of the code, you queue up a bunch of strings. So hash append, open paren, comma, s dot. That's first part of your string. I put another string in there. There's a name facility also in the template metaprogramming version of this. You can ask for the name of something. That solves the enum problem. But anyway, I can insert a string for that, and then I add the parentheses semicolon at the end, and I just say, okay, inject that, queue that up for the compiler to process. Now, because this can be really hard to debug, you can tag the thing you just queued with a name, whatever name you want. You just put a string there, and if there's an error that occurs, it will tell you, oh, it occurred with this tag. Maybe that means something to you. And then you can go say, oh yeah, that tag is this function that generated that part of the string. So that's the only reason for the extra parameter, is to help debugging, because this is definitely harder to debug if you use such a system. And then the token stream injection, you saw it, that's the exact same example as before. We use this this arrow operator. Now the arrow operator, like it's shown here, just immediately injects it after the const explorer evaluation. But sometimes that's not what you want. Sometimes what you want is, instead of injecting immediately, you want to inject it in the enclosing class. Right? Maybe you want to add some members to your class through metaprogramming. So you would have this notation, or in a namespace, or in a particular namespace. And Andrew Sutton actually had a need for something even more flexible, which is he wanted to be able to give you some meta info that describes where to inject the code. Okay, so he actually has implemented some of that stuff. All right, this is the overall picture of reflection in what is coming. Like I said, we're working on this. It's not going to be in C++20. I don't think so. It would take a miracle for it to be in C++20. I'm hoping in C++23 you'll have a good chunk of this. But you've also seen we already have some context for extensions, like the brace notation, context for brace, close brace, to do things right away. There's other extensions that we will want. And there's some time left? I do, great. I'm going to present some of these to you now. The nice thing about context repression, they're actually useful outside of reflection. Lots of them anyway. So we are actually currently already adding them to the language. In fact, the last meeting, I added the first one, which I'm going to present to you, which is dynamic allocation. And it's a paper I wrote with Richard Smith, Nina Rand, and Louis Dion. But I also should thank Anthony Polukin. Anyone, you guys know him? So thank you, Anthony. Because he's actually, I had a different proposal at some point that was much more limited than what I'm going to show you here. And Anthony said, no, you really should think about this a little harder. I told him what he wanted was impossible. He said, no, you should really do an extra effort here. He actually wrote a paper for the standard asking, revisiting the attack vector for this problem or something. And, he convinced me to look again, and he was right. We could do better, and so now I'm going to show you what you can do. So this part has been accepted by the evolution group. It still has to be accepted by the committee as a whole, but usually the hardest part is done. And the words for the standard are already ready. So what are we doing here? This is a really stupid function to sum up some numbers. You'd never do it that way. But what I'm doing is I am allocating some memory here, filling it up with numbers, and taking the sum of them, and then deleting it. If you do this using a new expression, right? So you actually have to say new some type and delete some, the corresponding pointer. If by the time you're done with evaluating everything, so there's no dynamic allocation left, then it's valid in a constant expression. You can do this as a constant, no problem, right? So now you have new and delete in the language in context for functions without an error. Right? If you try to C++17, this would give an error because sum13 is not a constant because new expressions are not constant. Okay, that's great. But new expressions, we don't use them anymore. We tend to use allocators, certainly for containers and so on. So this also works with containers. You can use this, but only the standard allocator. Okay, so the standard allocator you can use allocate and deallocate as long as by the end of the evaluation nothing is left. It's valid. Better yet, you can use the allocator trait. There's a function in there called construct. Construct is a little bit like placement new, except it doesn't lose the type. And because it doesn't lose the type, constexpr can actually do this. So you cannot use placement new in constexpr, even with these changes. But you can use construct, which is great, because once you have those things, we will be able to do containers, standard containers. There's one thing that's missing, is we need constexpr destructors, because that's where we're going to put our deallocation function. So we have added that also. So you, in C++20, barring any big surprises, you will have constexpr destructors and allocation, deallocation, and allocator traits. And you'll be able to do all of that. So now this is a very simple, not very useful class, but it shows how the constructor can do some allocation and initialize something. There is a function that actually computes the sum, and then you deallocate. And I can call this here in one set. So I construct it, and I call result, and then the destructor will be run. And because at the end of doing all this, there's no memory left, it's valid. Okay. So that allows you to write the containers. Now we still have to, we actually have to change the standard to allow you to use something like vector or string in the standard, right? P0784, which was the previous paper, the previous feature, it only gives you the tools. So we need to do some work. All right, so Louis Dion is working on that, and you'll be able to do this. So you'll be able to say, create constexpr functions that have vectors in it, and you will be able to just use it in context expression, as long as that vector is deallocated by the time you're done. All right. Now there's a funny story here. In C++14, the language a change was made for people to for compiler writers and actually for backend writers. When you use new and delete or allocators and deallocate, the compiler is not required to obey you. If they match, it's allowed to optimize it. And that's even at runtime. So when you call a new expression, operator new may not actually be called. A compiler can decide, well, I think I could allocate it on the stack instead, and it can optimize it that way. So what we're doing here, we're sort of mandating that optimization for constexpr. That's one way of looking at this. All right, so now we would like to do strings. And it turns out that what we have so far is not enough for strings. Anybody knows why? Strings do something really unfriendly to constexpr functions. Short string optimization. Have you guys ever heard of this? So a string, standard string, most implementations, what they do, so they have a pointer and a length in there, but if your string is very short, instead of using that pointer and length, they sort of put the short string directly in that same storage. Right? It's a nice optimization when you have lots of short strings, but constexpr doesn't like you to do weird tricks with pointers and reinterpret casts and so on. So we brought this to the guys who own the string specification in the standards. It's called the library evolution group. They look at how we could evolve all the library, and we said, we have these really neat features here. We'll be able to do some allocation at constexpr. I think we think you will like it, but what do we do about strings? I said, well, we really want to make it work, so let's work together. And so we work together, and we're adding one more feature, and that's probably going to be added at the next meeting. You can find the origins of this feature in P0595, but that's an old paper. What you're going to see here is actually a look into the future. So this, in about a month, this is going to be presented to the committee. In the constexpr function, remember, constexpr function can be called either at runtime or at compile time. You're going to be able to tell which of the two you are in. So there's a new magic library function, which is true if you're being evaluated because the compiler needs a constant, or if you're just being evaluated at compile time. Now, this is not the constexpr function itself, or it sort of is, but once the compiler has decided which it is, it knows whether it is true or false. So in the true case, we'll just evaluate it in the compiler. In the false case, it's going to be a constant false from the backend's perspective. And so it will optimize all of this away, and you'll just have this other branch here. So what is this particular function? It counts the ones in an unsigned value. There's usually an assembly instruction for this. Pop count is usually how it's called, right? And so you'd like to use that assembly function thing, but assembly is not valid in constexpr. So in the case we're in a constexpr function, I just use a slow but reliable algorithm that works with constexpr. So if I call it here with a 5, which 5 has 2 ones in its representation, right? The bit for 4 and the bit for 1. It will call this function, and in constexpr call will be true. Same with 7. But if I pass it a variable, I cannot evaluate it at compile time. And so it'll be done at runtime, and during runtime this will be false. But it will be optimized away, so it will just execute that ASM function, right? So you can see how this is something that could probably be useful for some of the functions you have, even if you don't use reflection. And so we're trying to move that early on into C++ 20 before we even have reflection. And in some cases, the standard won't actually tell you which it is. For example, here, a compiler is free to evaluate it at compile time or at runtime. And so depending which it is, you'll get a true or false here. In practice, I think all compilers will actually do this at compile time. All right. Well, so with this tool, the standard library guys said, well, we'll just don't use the short string optimization at compile time. And you will be able to use strings in your constant expressions. Okay, so that's nice. We can do allocation as long as you have deallocated everything. But a lot of people, they would like to have a stud string in ROM or stud vector in ROM, statically initialized. But it allocates on the heap, so how are we going to do that? Well, we can solve that problem with the things that we're developing here. And I call it storage promotion, and that's also something I'm hoping to get in Rapperswil, which is the next meeting of the committee. So what's going on here? I have a vector I fill it in with some data, and I return it. So there is some leftover dynamic storage. This can never be constexpr. So this should not be valid, right? Even with the previous paper, the previous feature. But I'm going to make it valid. And here's going to go work. First, I'm going to see this. I'm going to say, ooh, bad news, there's some storage left over. And the storage is in my compiler. How can it possibly be in my runtime? Right, that's the problem. That's why we had to have this rule that the storage has to be gone by the time you're done evaluating. Okay, well, let's try the destructor. So let's run the destructor here at compile time. Right? So I'm not actually destroying anything. I'm just trying it out as a constexpr evaluation. Good. Does that work? Right? So is it a constant expression? Yes. Okay, let's say it works. My vector has a nice constexpr destructor. It actually does things. Not only is it successful, but it actually deallocates all the storage. So if I were to run my destructor, it would deallocate everything. If that's the case, then I take that leftover storage and I move it from my constexpr heap, the one that's in the compiler, and I move it to the same storage that the variable vec itself is. So if it's a static variable, it becomes static storage. If it's a local variable, it becomes local storage, stack storage, right? But I still have the destructor of vec. So the compiler is going to say, well, don't run the destructor anymore, right? Because we're no longer really doing heap operation, right? Because it's on the stack or it's in or on static storage. And so this is a vector, a standard vector. I haven't changed the type, but its storage is no longer on the heap. It's now static. And when we show this to embedded programmers, they love it, because right now they have to write external tools to create all their tables, the data structures, and put them in ROM. And now they're going to be able to just write a constexpr function that does that and does exactly what they want with no external tools, no difficult to maintain programs. What do you think? Yeah. All right. So that will be okay. All right. Constexpr, we already mentioned, can be compiled. Can be evaluated at compile time or at runtime. Well, that's great, but sometimes you really want to make sure it happens at compile time. In particular, for reflection, right? Reflection, compile time reflection only makes sense at compile time. Those meta info values that we have, they have no meaning at runtime because they refer back to the compiler state. The compiler is no longer there at runtime. So Andrew and I are proposing, again, this next meeting, a modification of constexpr where you put an exclamation mark at the end. And what that means is, if it's not a constant, it's an error. Okay, so unlike constexpr, if it's not a constant, then you wait till runtime to evaluate it. It has to be constant. So you can call this square function with 128. It's going to evaluate it. Sure, that's a constant. Fine, that works fine. But if you call it with a variable, compile doesn't know the value of that variable. Maybe x was modified since I initialized it. So that will be an error. There's an interesting little quirk when you compose these. So a same function here, so it computes a square, but I want to write a function that calls another, so a constexpr function that calls another constexpr function, both with exclamation mark. Well, this would ordinarily be an error because n is a variable, I can't evaluate it. But if you have a call to an exclamation constexpr function, you are allowed to call another one without a constant, because I know that ultimately I will be called as a constant. Does that make sense? Yeah, otherwise you could not compose these things. On the other hand, if I were to call this square function from a regular constexpr function without the exclamation mark, then it doesn't work, because the problem is that this one could be evaluated at runtime, and now I really don't know what this n is. So this is going to be an error at compile time, because I don't know what square n is, and square is supposed to be a constant. All right? Turns out that it's nice to have something similar on variables. We mostly wanted it for functions, but it turns out it's nice for variables in particular. People use macros for constants still today because if you define a constant as a macro, it's an R value. And there's really no way to do that in the language today in other ways. So if you use a constexpr variable, constexpr x equals 42, that is an L value. So if you were to pass it to a function that has a reference, like it takes it by reference, the compiler has to spill that value into your memory and then pass a sort of a hidden pointer to it. And we don't want that. We'd rather have it initialize a temporary and pass a temporary. So constexpr exclamation mark on a variable just means that you only use it as an R value. It never takes, that variable never goes into memory. Just like context per exclamation mark functions never goes into memory. So basically, context per exclamation mark is a big step towards being able to move away from macros. And that's actually a goal of the committee in the long run, to some degree. We're interested in having fewer and fewer dependencies on macros, and this feature will help a lot towards that. Okay, that's actually what I had for today. So thank you for having me over. I did present a talk, and go back in time, that had this first slide, reflective metaprogramming in C++. This was in 2003 in Oxford. And I have, it actually was presented both to ACCU and to the committee. And if you're interested, you can go check out the slides for that and compare to what you saw today. Back then, it was just my project. As you notice today, it's a project of a lot of people, right? Andrew Sutton, Harp Sutter, Louis Dion, Matus Shoshlik, and all those guys contributing to this. And I'm hopeful you'll see this fairly soon. I hope you'll be excited about it. It'll be useful to you guys. If not, come and tell me what you need. I'd like to hear from what real programmers need to have in the future of the language. And one more thing. I wrote that templates book. There is, a few months ago, we finished the second edition. I happen to have a copy here. And let's see. I'd like to give it to one of you. I thought there's enough pages I could give you, each of you one page, but you wouldn't be happy if I did that. So I'll give it to one of you. But how are we going to give it? So I have a little idea. I asked the officials of the committee how many people were at the last committee meeting. And at first, there were a little bit fewer than you guys. There were a lot, but fewer than this room. So it's a number less than 500. If you meet me anytime today, come and introduce yourself. Say hello. I'd like to meet you. And if you want this book, tell me a guess as to the number of people that were at the last committee meeting. I'll give you a hint. It's more than -1 and less than 500. Actually, I'll give you a better hint. It's less than 300. Whoever is the first to find that number, get the book. So please guess it right, because I don't want to carry it back in my luggage. And thank you for having me over. If you have questions, I'll be happy to answer them.
Hello, thank you for the talk.
Thank you.
On your slide, we have this start isn't context per call. So I would expect that code to fail to compile, because you still have SM in your context per function, even though it's in a branch which is always false. So shouldn't it be context per if instead of just if? Or I mean, if context per this new construct we get in 17?
So we have been evolving to where context per functions no longer put structural constraints. So for example, it used to be that you couldn't have a throw in there at all. Nowadays, with C++14, you can actually have a throw as long as you don't evaluate it at compile time. We're going to do the same for ASM. I think ASM is one of the few things that still, you can't even have it. But that's part of the change. We're going to allow ASM to appear there. You just cannot evaluate it if you need a constant.
Okay.
Because if context per doesn't work, and the reason why it doesn't work is that call. Let me try to bring that slide back up here. Come on. I'll try to find it for you. No. Here it is. You see, we don't know when we parse this this function, right? If context per is something that happens as parse time. So if you had if context per, as soon as I see it, I need to know the value, but I don't know. It depends on what you pass in as word, whether you pass in a constant or not, right? And so I don't know. So we cannot use if context per. It has to be an ordinary if. But you're right that today ASM here, I believe, is not valid at all. You'd get an error, and we're going to change that rule. So ASM and a few other things actually, probably gotos and so on, will be valid as long as you don't evaluate them.
Actually, use them. Okay, thank you.
You're welcome.
I have actually two questions that are similar. Well, about using new in and a std vector in a const_expr functions. Well, for it to work, a compiler needs to be statically checking if we have gone out of bounds when it evaluates a function. And basically that means that the pointer representation should be not a simple void star and something else. Am I right?
You're absolutely right. So the const_expr implementation of compilers is an interesting beast. It does not represent pointers as just an address. It has a sort of a fat representation, so it can do what do you call it, bounds checking, like you say. It also has an object representation that keeps the types around so that we know what we're pointing at. And it tracks the lifetime of the issue, so you don't try to read from uninitialized stuff. So it's actually, const_expr evaluation is a lot more efficient than instantiation, but it's not efficient. It's still a heavy process. It's an interpreter, but it's not, since C++ is not designed for interpretation, like your typical Python interpreter would be way faster than this. But it's fast enough. I can do about 1 million iterations, 10 million iterations per second in my compiler.
Yes, thank you. And from it comes second question. Well, you told about a possibility to return a const_expr std vector from a const_expr function. And, well, since the representation is different, how is that achieved without, well, do compiler need to convert somehow from a std vector in a const_expr function to a std vector in a real code?
Yeah, so it has to, so the interpreter has its own sort of virtual machine, if you will, that it runs in. And so it will have this storage there. It will have to copy it and turn it into sort of the equivalent initializer in static storage. So it does have to do that work. It's not very difficult to do. We for example, do that already for initializer lists. You put an initializer list there. We sort of copy all these expressions and put them in static storage. And then we pass pointers to an initializer list object. It's a similar issue.
Yes, I get it. Thank you.
You're welcome.
Hi. Thank you for the talk. You showed some metaprogramming syntax, and personally, I see a big drawback of it because it pretends to be common C++, but it is not common C++, and it really might confuse the reader of the code. That's because I like template syntax of metaprogramming, because when you see it, you understand that it is metaprogramming.
Okay. I understand, because you're not the first person that tells me that. You're the second person. So it's true that it's fairly easy to look over this code, but there's a few markers, right? You have this const_expr brace notation. You have possibly an injection notation. I think personally, and the majority of the committee is with me, and frankly, I've had a lot of people giving me feedback of this over the years. For most people, they would actually prefer that, but I do know that it's not universal. There's some people who really like template metaprogramming. But the problem with template metaprogramming, even if you prefer the notation, is it doesn't scale, right? Because of the storage problems that I mentioned earlier. We cannot reclaim the memory of template instantiations. So you could perhaps think of building something like this on top of a template notation, but the current preference of the community as a whole, we think, is something more like C++, like standard C++.
Thank you.
Thank you for the question.
Hey, did you present basically examples from the entirety of the proposal that we'll hopefully see in 2023? For example, I'm asking about other features. Is there, for example, a way to handle compilation errors? And more specifically, is there or are there plans to support stuff like when I call a method from a class and the class doesn't have this method, is there a way for me to handle it at compile time and generate this method? Like
generate the method? Right now, I believe there is no such thing in the P0914 proposal, and we're not adding any functionality to that. So generating a new definition from a declaration that you have to reify, I'm not aware of how to do that. But I think there is a desire to be able to do that. See, we're building things incrementally. That's why one of the things one of the points I was trying to make is that you already will have some things in C++20. They're not reflection, but they're already useful for you. And then in C++23, hopefully we'll have more. And as we explore the ramifications of P0194 as a TS, we'll hopefully find maybe, I mean, you should give feedback on that. So contact me and tell me, show me a piece of example. Invent your own code, if you will, your own syntax, and tell me, I would like to do this. Because if I have this, a lot of this feedback, or send it to me or to anybody in the committee, that is helpful for us, right? When we say discussions, like, you know, we didn't think about this issue, and we know there is a community out there that wants that.
I have two questions, and first of it is, why do we need const export vector? Because vector is not a part of core language. It's a data struct from libraries. So when we speak of metaprogramming, we want to generate code, but vector is not part of code. C++ can, we can imagine C++ without a vector, but you took it into const export world. It's a completely different world. Why?
Well, my original proposal, remember how I thanked Anthony Palukin for helping me? My original proposal was to make a specific container for the const export world, one that's just for const export. But the nice thing is, const export functions can run at compile time or runtime. So if you can share your vectors, you can make functions that work in both worlds. So by not having a new type for const export, a new container type, it's more flexible. And we can do it as a compile, so we give you that feature. And it's very useful to have containers when you do metaprogramming, right? Because you want to represent lists of members, lists of functions, lists of parameters, lists of variables. So, you know, it's nice to have a container type. So why not use a standard container types instead of having a totally separate set of things in the const export world?
And the second question, thank you for your answer. And the second question is, when you generate some code by metaprogramming functions or expressions, there is a problem of calculation order. So when you generate some code, you can use it in other meta expression.
Yes, it's a good question. It's a good point. So that is that's going to be, I think, one of the biggest challenges in using metaprogramming, which is you're going to have ordering issues. You cannot, for example, call a function that you haven't defined yet. So the way we're looking at synthesis is that you still have to take care of that manually. Right? You cannot say, well, I'm going to write a call to a function, and I'm going to later tell you what that function is, because we have to be able to parse things. So that is, in a way, we would like not to have this order dependency, right? Because we're no longer in a source code context. You would think that we should be able to create just a graph. And that's actually something that we have talked about. Would it be nice that you could create the AST directly, programmatically? But it's a heavy thing to do. We're looking at it as a possible additional way of synthesizing code, is that you would actually be able to construct AST. There's a couple of problems. One is it's not terribly fun to do, right? You have to little by little construct these things. It's not terribly fun. The second one is that all compilers have very different approaches to ASTs. In fact, until just 1 or 2 years ago, Microsoft had no AST. So they had a compiler without AST. So if we were to impose, you know, how to construct an AST so you can do orderless programming, it might be a problem. We're looking at it, but I'm pretty sure that will not be for C++23.
Thank you very much.
You're welcome.
Thank you for this awesome talk. I think one of the most underappreciated nifty little things is const export exclamation mark for values. I really like that. My question was regarding difficulties. Even now, difficulties in template metaprogramming come from specializations of templates and visualizing gradually how a template is actually specialized. Do you think we have a chance in tooling to be able to visualize the reflective parts? For example, if we do a meta-info traversal, is there a chance in tooling space to see how this actually is traversed, the types are traversed, and being able to debug such meta capabilities?
That's a really, really good question. So with template metaprogramming, debugging is difficult. With this, debugging might be difficult. The advantage we have, though, is that we are now in the same sort of world that we are at runtime. So I could imagine that over time, we will have context per debuggers. Now, that's not going to come soon. Now, originally in this talk, I had another proposal, which I'm going to move forward, but I wasn't sure I could fit it. I've been trimming this talk to try to fit it in 2 hours, and it turned out to be fine. But when I tried it a few times at home, it took a little longer. And one of the things that I had in there is a facility to basically have a context per print, or context per report, so that when you run a context per function, you could put this magical function in there, and it would actually output diagnostics without giving you an error. Just continue, but you'll be able to see, oh, it's basically like debugging with printf. You can see what's the state of my program. Please tell me where, something is going wrong. I don't know where. Let me print something to see what's going on. And so that's also something we're trying to do, probably for C++20.
Hello, thank you for the talk. The question is, when you mentioned context per exclamation mark, you mentioned also that basically the arguments of that context per exclamation mark function will be context per, or like will be treated as context per. I want just to clarify, will we be able to use them as template arguments, or like in any other environment where only context per evaluation is allowed? And especially if that includes strings, string literals that are notoriously like bad for templates.
Yes, so the answer is yes. You will be able to use any. In fact, you can already do that today with regular context per functions, but you're just not guaranteed that at the end you have a constant. Here you'll be guaranteed to either have a constant or an error. It'll never be runtime. But so yes, you will be able to do that.
So we will be able to use them in not the context per call, but like the argument of context per function. We will be able to make basically like a std array with n as an argument, where n is...
oh, no, okay, sorry, I misunderstood you. No, sorry. I'm so sorry. Now I understand what you mean. So let me repeat the question and so everyone understands. Imagine a context exclamation mark function, void f int n. We know that when it's going to be evaluated, it's going to be a constant. So why not allow std array of int n, with that n being that parameter, right there? Right? I think that's the question. And unfortunately, it can't be. Remember, I mentioned that paper P0993. I think that's a paper. Andrew explains why we cannot do that. The evaluation of a context per function is completely separate of parsing. So when we do evaluating, the compiler doesn't have side effects. It's just an evaluation, and we don't start. You see, the instantiation of that array, that's actually a part of the parsing process. And the context per evaluation is something that's separate. It's almost like this virtual machine is on the side. And unfortunately, we cannot do that. I mean, we could, but it would completely require re-architecting of compilers. And we will never be able to sell that. I'm really sorry, because I know a lot of people would like to do that.
Thank you.
I have a question regarding this context per call.
Yep.
From my point of view, there could be another mechanism for the same purpose, which could solve the same problems. I mean, this is some kind of overloading for const expert functions.
I knew you were going to say that.
Have you considered this?
I have. It doesn't work.
Why?
Because if you want to do overloading on it, you are going to have to create new types. You're going to have to move the const expertness of the parameter into the type.
Okay.
When you try to do that, you get exponential explosion of your signatures. Right? You're going to need two
signatures. Yes,
you're going to do two signatures. Except that if you have two parameters, you need 2 to the power 2 signatures. If you have 3 parameters, you're going to need 2 to the power 3 signatures, and so on. We tried it. I mean, this comes over and over. People would love that because they feel it's more natural. It turns out this scales. It's actually easier to use. Your code is easier to write. So it's a great idea, but I encourage you to try it out. Write your code and see and simulate the compiler, and you'll find out it does not work. I mean, it works. You can make it work, but it's not pleasant to use.
Okay, thank you.
Thank you. It's a good question.
Well, thank you for previous answer. I was going to ask something similar, but continuing on is in conceptual call. Shouldn't this not be a function, but operator or something? Wouldn't we get some problems with one definition rule if in conceptual call is a function, actual function in the std namespace?
So it's a good question. So the question is, would this create one definition rule problems? The answer is no, because one definition rule is really about parsing. And remember, as I mentioned earlier, context for evaluation is outside of parsing. So it means the same thing in both contexts. It's just the evaluations are different. Now, although, despite that, the original proposal, remember, in fact, maybe I can go back. I don't know if I can get, oh, here. If you go to this paper, you will find an operator and not this magic function.
Yes, well, that's basically why I asked it.
Yes,
so
yes.
And
the reason why it's a magic function now instead of the operator is that this was presented and was basically, the idea was approved by Evolution a while back, a year ago, maybe more. And the only thing they asked me was to change it to be a function.
Wow.
And I think actually I like it because the function has a better name. I like the name.
Yes. Okay. And another question. Now we have some functions in a library, namely mass functions that are required to be const expert and are basically should be implemented in that way, because in runtime we call some assembler functions mostly, and in compile we do some magic tricks. And is there a guarantee that the compile time evaluated result will be the same as the one evaluated at runtime because of floating time number precision issues?
Oh, yeah, that's a good question. So the question is, can we actually guarantee that you get the same result at compile time as at runtime, especially if you work with floating point numbers, right? For example, the rounding behavior of floating point numbers can change at runtime. So the answer is no. Unfortunately, you don't have that guarantee. It's not always easy to ensure that guarantee. It's up to the programmer to make it as good as possible.
Well, is that guaranteed by a standard for
no,
standard mass functions?
It is not. There is a defect against the standard about that, as if I remember correctly. Where the library actually has some issues in general with the specification of const expert, and they're looking at that. In particular, I know there is an issue, and I don't know if that's the library or the core language, but about whether something could be const expert if you have functions that call the floating point environment settings. But it's a difficult problem. So floating point and const expert. If you really care about runtime rounding mode, you probably do not want to use const expert for that. But a lot of people are happy to have something that's good within 1 or 2 bits. So it's a trade-off. Yeah, but it's a good question. All right. Well, thank you very much. Come and talk to me and make your guess.